The law of cosines is, well, unfortunately, a little more complicated than the law of sines. But the law of sines does not apply to all of the congruence relationships. The side-side-side relationship and the side-angle-side relationship require the law of cosines because there simply isn't enough information in the relationship of the law of sines to address these particular situations. First of all, because the law of sines requires you to know the measure of at least one of the angles along with the length of the side opposite that angle. In the side-side-side relationship, you don't know any of the angles. In the side-angle-side relationship, you do have the lengths of two sides and one angle, but it is the lengths of the two sides on either side of the angle. You do not have the length of the side opposite that angle. So again, unfortunately, the law of sines will not apply to these because in neither case do we have the length of one side and the measure of the angle across from it. There are actually several forms of the law of cosines depending on which two sides and which angle we are talking about. So for a triangle that again has angles A, B, and C and side lengths little a, little b, and little c, such that the angle and the side with the same letter are opposite the triangle from each other. The law of cosine says that the length of angle of side A squared is equal to the length of side B squared plus the length of side C squared minus 2 times the length of B times the length of C times the cosine of angle A. Yikes, that's a rough formula. The other two forms are very similar, and it helps if instead of reading this with A's, B's, and C's, if you read it as thinking of which side are you looking for and which two sides and angle do you have. So if you're looking for side B, but you have A and C, then B squared would be by itself, and on the other side you have the sum of the squares of the two sides that you do have, minus 2 times the product of the sides that you do have, times the cosine of the angle opposite the side you're looking for. When you put it that way, it doesn't really sound much better, except that that description applies to all three of the formulas without having to remember A's, B's, and C's all over the darn place. So again, the square of the side we're looking for is equal to the sum of the squares of the two sides we have minus 2 times the product of the two sides we have times the cosine of the angle we have. Yikes. These three forms are useful if you are trying to get the length of a side, which means they are useful for the side-angle-side relationship. So if we're dealing with a triangle where we have the length of a side, then the angle, then the length of the next side, these are the forms that we would use. Each of them, however, has an alternative form, which is achieved simply by solving for the cosine of the angles. So the first one, if we were to solve that for the cosine of A, which I will leave you to do if you wish to show it, the cosine of A then would have to be A squared minus b squared minus c squared over negative 2 times b times c. The second formula can be solved in the same way for cosine of b, which would result in b squared minus a squared minus c squared over negative 2ac. And in the same way, the third, cosine of c, would be c squared minus a squared minus b squared over negative 2ab. These three forms, they are equivalent to the three above, but they are just reworked to solve for the cosine of the angle. So these three are particularly useful in solving when we have all three sides, A, B, and C, little a, little b, and little c, and can just plug them into these formulas directly, and that would give us the cosine of the angle, at which point we can use the arc cosine, if need be, to get the length of the, or the measure of the angles. So these are used when we have all three sides. So let's try an example of each. We'll start with the side-side-side relationship, which would use those three forms that we just dealt with. So we're going to look at a triangle that we have side lengths of little a equals 8 feet. That would put angle A across from it. Little b equals 19 feet, which would put angle B opposite the triangle from that. And little c equals 14 feet, which would put angle C opposite the triangle from that. So, we have all three sides. We can find any of the three angles from that. Let's try the cosine of b, which should be b squared minus a squared minus c squared over negative 2ac, where we have the lengths of the three sides, so all we have to do is put them in. Side B is 19, so we have 19 squared, minus side A squared, which is 8 squared, minus side C squared, where C is 14, over negative 2 times the length of side A, 8, times the length of side C, 14. And again, the calculator is our friend here. There is absolutely no shame in using it. That's why we have it. Some of these are going to get nasty, and to be honest, in order to finish solving this and get the measure of angle B, we really have no choice. We really have no choice but to use the calculator anyway. So we're going to go to that and just plug the whole thing in at once. And that whole thing comes out to be negative 0.45089, etc. Now, we're not going to round this off, because we aren't done quite yet. What we now have is that the cosine of b is equal to negative 0.45089, etc. And the only way we're going to get angle B out of this is to use the arc cosine. So B would have to be the arc cosine, or the inverse cosine, if you prefer to use that, of our previous answer, which is why I haven't rounded it yet. So we go to our calculator and we do the arc cosine of our previous answer. And that comes out to be 116.800, etc. degrees. And now it is acceptable to round it. And given the 2 zeros after the 8, we can probably get away with calling it 116.8 degrees. And that is the measure of angle B. At this point, we can find the measures of angle A or C by using the, again, law of cosines, or at this point, we can actually switch to the law of sines if we prefer. And the law of sines actually is a little bit shorter and a little bit nicer because we don't have to use any of the arc functions. But the idea is now we have one of the angles, angle B, and the length of the side opposite that angle. And that's what we need to make the law of sines work. And once we have a second angle, we can get the third by simply saying they must all be equal to 180 degrees in total. So we'll be able to get the third angle. So the law of cosines is a little bit complicated in its formula, but the nice part of it is we only need to use it once. Once we have any angle measure and the side length across from it, we can go back to the law of sines, which honestly is a lot easier to work with. So I'm going to go after angle A now and say that the sine of angle B over the length of side B has to be equal to the sine of angle A over the length of side A. So the sine of 116.8 degrees over 19 has to be equal to the sine of A over the length of side A. Well, I guess we are going to have to use an arc function anyway, but it's still probably faster to do this. So, again, with a little bit of algebra here, to solve this for the sine of A, we would have 8 times the sine of 116.8 degrees over 19 is equal to the sine of A. Our trusty calculator is our best friend here. So this left side comes out to be 0.375, etc. And that is equal to the sine of A. Therefore, A would be equal to the arc sine of 0.375, etc. Which gives us 22.075 etc. degrees. We can round that off to call it 22.08. Now that we have the size of two angles, we subtract both of them from 180 degrees, and that will give us the measure of angle C. So again, 116.8 degrees plus 22.08 degrees plus the measure of angle C is equal to 180 degrees. So again, a little bit of solving here will give us that angle C is going to be 41.12 degrees. And thus, we have solved the triangle. Not horrible. Certainly a little less friendly than just using the law of sines directly. But we can get there.